This is a continuation of the lesson on equilibrium constants. So before we go on to a slightly more complicated example, let's look at what happens or what it means when you get these different values for your equilibrium constant K. So a K value greater than 1 means that the equilibrium is far to the right. So it's like literally mostly products in the beaker or the flask. Okay, so even though it's in equilibrium, the equilibrium exists as lots of products. Okay, a K value less than 1 is going to be the opposite, so mostly reactants. So even though you have lots of reactants around and only a few product molecules, it's still in equilibrium. Okay, this is slightly different than the idea for Q, which is your reaction quotient. So Q is found the same way using the same type of expression, so the concentration of your products over your reactants. But in that case, you can use Q to predict shifts. And so when we're looking at Le Chatelier shifts, especially if you're given concentrations, you can predict which direction equilibrium will shift based on having a reaction quotient and a KEQ value. So if your reaction quotient is less than your equilibrium constant, in this case you would just simply follow the mouth, or the, you know, how we used to learn that greater than less than is following the alligator. So if the equilibrium constant is greater than the reaction quotient, then that reaction is going to shift to the right because it actually needs more products to be made. If the two are equal to each other, that system is in a wonderful, lovely equilibrium. And if your reaction quotient is greater than K, then that reaction will shift to the left because that means that you actually need more reactants in order to reestablish the equilibrium. So again, reaction quotient is not at equilibrium. That's really more looking at how stresses are going to cause shifts to happen, whereas your K value, your KEQ, is looking at what happens when the system is in equilibrium. Okay, in the second example, we're going to look at how we can use calculating various K values and manipulate them in order to predict other ones without having to do quite as much math, just simply by thinking about what the question's asking us and which side is the top versus the bottom of the expression that we would want to use. Okay, so in this equation or in this scenario, instead of concentrations, we are given pressures, partial pressures of the different gases involved in this equilibrium system. So because these are all gases, then pressure will affect all of them. And remember that just in general, when you're thinking about Le Chatelier shifts, if you increase the pressure on a system, it's going to shift in the direction of less moles of gas. So in this case, an increase in pressure is going to cause a shift to the left. So ideally, the numbers that we find should help kind of support that idea. So if we're going to calculate a KP, remember it's the same general idea, but we're using our pressures instead of our concentrations. So in this case, we're dealing with this equation here. So we're always going to put our products over top of our reactants. So we have our pressure of nitrogen monoxide, and that is going to be squared because there is a coefficient of 2 in front of it. That's going to get multiplied. Oh, sorry, that's the wrong 2. It's this 2. And that's going to get multiplied by our other product, which is chlorine gas, and there's a coefficient of 1, so it'd just be whatever it is. Okay, on the bottom we'll have our pressure of NaOCl, and that is going to be squared as well because of this 2 in front. Okay, so to make that simpler with numbers, the pressure for our nitrogen monoxide is 0.050 atmospheres. That is going to be squared and multiplied by 0.30 atmospheres. That is all, that entire product, remember be careful with your calculator, is going to be divided by 1.2 atmospheres squared. Okay, so if you do all of that math, you should get 5.2 times 10 to the minus 4. Okay, and remember with K values, in this case, this is not the same K as rate constant K. This is a capital K. So with these K values, we typically don't use units. We just use the value and its relevance to the number 1. So since this number is a lot less than 1, our K value being less than 1 means that our system has it's favoring our reactants, right? So we have more reactants in the equilibrium system and less of our products. Okay, so that's what we're saying right now. Remember, we said that if we increase the pressure, it's going to move in that direction. So now let's see if any of that makes sense. Okay, so moving up a little bit. The nice thing about once you've calculated the Kp value for something, then if you're doing some simple algebraic manipulations to the balanced chemical equation, you can do those simple algebraic manipulations to the value you've already calculated without having to recalculate everything. So you'll notice that our initial reaction had NaOCl as the reactant, and here all we've done is flip it around. So in this reaction, everything is reversed. So in order to find the Kp of this equation, all we really need to do is use the previous answer from letter A. So it's going to be 1 over the Kp that we calculated in A, or 1 over 5.2 times 10 to the minus 4. And that gives us 1920. You should find that if you flip your equilibrium constant pressure expression over, so this thing right here, if you flip that upside down and re-plug in all of your numbers and do the math, you should still get 1920. But if we can just recognize that we've just inverted the equation, you can just simply invert the number that you've already calculated. Okay, that's not going to be true for our Kc value, however, because you're going to have to refer back to the equation up here where we were dealing with the ideal gas law. So this one here. Okay, so I'm going to rearrange this equation for Kc because remember, that's going to be our sort of real equilibrium constant. We can use that interchangeably with K and Keq, but we can't use Kp that way. Okay, so we use that expression or that equation to find Kc based on a known Kp. Okay, so in this example, we're going to be using the same equation as in B, so I'm going to use my Kp of 1920. So if I rearrange my equation, I have Kc is going to equal Kp over my ideal gas constant, or my universal gas constant, my temperature in kelvins, and that's going to be raised to the change in moles of the system, right? So in this case, I have 2 moles of product, and I'm just looking at the coefficients here. I have 2 plus 1 moles of reactants, giving me 3. So my change in moles, going from my reactants to my products, is a change in -1. Okay, so that's going to be a -1 power there. All right, so again, since I'm using the same equation as I had in B, I'm going to use that Kp value, and then I'm going to put that over 0.08206. That is the universal gas constant. That's something that you should be able to look up. The unit in this case is liters, atmospheres, moles, and kelvins, but that works because my pressure was initially given to me in atmospheres. Then to convert temperature in Celsius to kelvins, you add 273. So 35 plus 273 is 308 kelvins. And we are going to multiply all of that, or raise it all to the power of -1. When I do that, we get 48527. We can also use the same algebraic logic to complete the last one. So we have re-flipped this equation around. So since I have my actual Keq value, my Kc, remember, is my equilibrium constant, then again, by the same logic as in B, then my Kc for that direction is going to be 1 over the Kc in the other direction. So I just calculated that as 48527. And so that equals 2.06. So I'll round that to 2.1 times 10 to the minus 5. But notice we also multiplied all of our coefficients by a factor of 2. So when that happens, that's an example of this situation here where you've got everything multiplied by an n. Oh, sorry. This situation. My apologies on that. So in this case, n for us is 2. So the last step for this would be to also square the answer to account for the doubling of all of our coefficients, and we get a final answer here of 4.2 times 10 to the minus 10. Okay, so again, what we're looking at is the relationship really kind of between A and D, representing the forward reaction based on the description in the actual verbiage up there. And then for B and C, we're looking at the pressure constant and the equilibrium constant with respect to the reverse reaction. So, like I said, you should still see something very similar where, as far as justifying what we know about our system. So in the case of our reverse reaction that we got for C, this value is much greater than 1, and this value is much less than 1. So both of these situations show that this particular equilibrium system is favoring NaCl. Okay, so because NaCl is a product in this case, greater than 1 means it's got lots of product. And in D, it's still favoring NaCl because there's a whole ton of reactant as compared to the amount of products. So even though we flip things around back and forth, you're still saying the same thing. This equilibrium system is going to have lots of NaCl. It's going to have some nitrogen monoxide and some chlorine when it's established in equilibrium. But either way, you've got a great abundance of the NaCl present. Okay, I know that seems like a lot of mumbo jumbo right now, but I just wanted to do that as an example, and then I've got a few problems for you to try. Please refer back to Canvas for those.